In this video, we're going to look at what happens when a wave comes to a boundary and continues on. So we'll be looking at the transmission of waves at boundaries. Now, if a wave comes to a boundary, some of it may be transmitted. If it's transmitted, then it just continues going like it was before. However, the speed of the wave in that new medium may be a bit different to how it was in the first medium. If waves move to a more dense medium, a kind of heavier medium, then they start travelling slower and their wavelength actually gets a bit shorter as well. If a wave goes to a less dense medium, so like it's travelling from a really fat rope and it goes into a really skinny rope, it then starts to travel faster. So often you get a combination of reflection and transmission at a boundary. So there's a nice example of that here. So what you can see here is a pulse going from a low density medium to a high density medium. So let's first of all concentrate on that transmitted pulse. You can see that the pulse, when it gets to the more dense medium, actually has a shorter wavelength. It's a smaller pulse. You can also see that it's moving more slowly and it continues to travel on the same side of the piece of rope. Let's now have a look at that reflected pulse. In this case, the pulse is reflected back on the opposite side of the piece of rope. That's because this more dense medium is acting in the same way as a fixed boundary, and it causes that wave to undergo a phase change. What you can see now is a pulse moving from a more dense medium to a less dense medium. When we look at that transmitted pulse, you can see it actually spreads out. The wavelength gets longer when it goes into the lower density medium. You can see it doesn't undergo a phase change, the transmitted pulse. It continues to travel on the same side of the piece of string. And the other thing you can see is that it actually starts to move a little bit faster. It's a bit hard with the perspective in this case, but it does start to move faster when it gets to that less dense medium. If we now concentrate on the reflected pulse, you can see that it's reflected back on the same side of the piece of string. So that less dense medium is acting like a loose end, and so there is no phase change in the reflected pulse. So we've seen that as a wave moves from one medium to another, its velocity will change. If it goes to a more dense medium, it will slow down. And because of our equation v is equal to f lambda, when it moves from one medium to another, the frequency doesn't actually change. So if the velocity decreases, lambda, the wavelength, also has to decrease. So this is why waves get more compressed when they move into a more dense medium. If it moves into a less dense medium, then it travels faster and the wavelength spreads out. So how do we apply this all to speed cameras? Well, speed cameras use a radar system. Radar stands for radio detecting and ranging. So it uses radio wavelengths to send out a signal which is reflected off your car, and it then detects this signal and measures the frequency that it records. It can use that frequency to calculate your speed. So in the next video, we're going to be looking at the relationship between the frequency of a reflected wave and the speed of the object which is reflecting that wave. So this is known as the Doppler effect.